Hello everyone. In this module, we are going to look at two improvised versions of policy gradient algorithms for aligning the language model to human preferences. The first of them is called the Proximal Policy Optimization Algorithm or PPO, and the other one that we will be looking at is what is known as DPO or Direct Preference Optimization. These are the two very popular algorithms that are used currently for aligning the autoregressive language models to a particular preference that is given by humans or verifiable data. Now let us start with proximal policy optimization or PPO. So recall that in the RL framework, a language model is viewed as a policy, a parameterized policy denoted by pi theta, and policy gradient algorithm is used for alignment of that particular policy. That's what we saw, right? So we saw that the parameter update. So what was the policy gradient algorithm? The policy gradient algorithm effectively updates the policy using this particular gradient update, where theta represents the parameters of the policy given by doing a gradient ascent on an objective function j theta, where we obtained an estimate for the gradient of the objective function, which was the discounted return. We saw that this was equal to the expectation of a trajectory coming from the policy, and we had gradient of log of the policy. Policy always is a distribution of actions conditioned on states. We saw this times the advantage function. So this was the definition of the gradient of the objective function that would be used in policy gradient theorem, right? So now if we approximate this expectation using the law of large numbers, sample averages, then rather let's say suppose G hat is an estimate, is a sample estimate. G hat is a sample estimate for the above gradient. In that case, we have G cap to be equal to 1 by T equal to 0 to capital T minus 1, the gradient of log of the policy. In this case, this is a transformer based language model, times the advantage function, right? The estimated advantage function, where A cap T is the estimated advantage and AT comma ST are the actions and states coming from the rollout, are the actions and states drawn from the rollout. So what is a rollout? A rollout is enacting the policy in the RL framework, but in the case of a language model, what we are doing is giving a particular prompt and generating responses. Right? We saw how to model a language model in terms of the actions and states within an RL framework in the last module. So these are the rollouts. So these are the actions and the states that are drawn from the rollout from the current policy. Right? So this is the sample estimate of the above gradient that we need. Okay. So now, while this can actually solve the problem in the sense that one can compute all the terms that are here, because one can evaluate the log likelihood of the policy, which is nothing but the logits that we get at the output of the transformer. The advantage function can be estimated using generalized advantage estimators, and which means that one can take the gradient of log of the policy using the usual backpropagation algorithms. So this estimator for the gradient that we need for updating the policy can be obtained. However, this is the naive policy gradient algorithm which can be used to update the policy. So however, what is known is that this estimator is on policy, which means that the above estimator for G, right, is on policy implies that it requires fresh samples for each update from the current policy. Okay. Now, what does this mean? If you look at this expression here, the rollouts or the actions and the states that we are obtaining are actually from the same policy that we are trying to optimize pi theta, right? In the context of language models, what is happening is that one would input a particular prompt and get the corresponding response. So by giving multiple prompts as inputs, one would obtain multiple responses as outputs, and this would constitute action and state pairs, state and action pairs that would be the rollout for computing this gradient. Now the issue with that is it is from this same policy that one is obtaining the rollouts that is getting updated as well. So every time a gradient step is taken, one needs to obtain a rollout from the exact same policy that is getting updated, and these sort of updations are called on policy methods because the rollouts are coming from the same policy that is getting updated via the policy gradient algorithm. Okay. Now, what is the issue with this? The issue with this is, now if you start sampling from the exact same policy before each of the updates, okay, now what happens is that this process is extremely expensive because one needs to collect the same policy, collect the rollouts from the same policy that is getting estimated, that is getting updated. The second problem is that it will increase the variance because every time a new trajectory is obtained, it is only used for one update, and the next time once the policy is updated, a new trajectory is being sampled. Okay. So what would one like is to reuse the trajectories which are collected from an old policy, okay, and use those as data while updating this current policy. So basically what we are talking about is that instead of having on policy updation, we would like to see if it's possible to use a different policy for collecting the rollouts than the one that is being updated. Okay, turns out that this is possible by using a well-known statistical technique called importance sampling. So let us look at what importance sampling is all about. Importance sampling. Now, importance sampling is a generic method in classical statistics that is used to evaluate expectation of a particular function. Okay, what is the problem? The problem is to compute the expectation of a particular function of a random variable f of x with respect to a distribution while x is coming from px. So this is the problem that we are interested in. If this is the problem that we are interested in, okay, how do we represent this expectation? So expectation of a function with respect to a distribution px is simply given by assuming that the density function that we have, the random variable that we have is a continuous random variable, is equal to integral px times fx dx, and this is over the sample space. Now suppose qx is another distribution, qx is another distribution on the same random variable x. If this is the case, then what I can do is that I can represent the expectation of this f of x with respect to px as the follows. So I will simply multiply and divide this particular integral by qx. Now because qx is a density function, it is always non-negative and the integral does not change if I simply multiply and divide the integral with this particular function qx. Now what is this equal to? If one closely observes it, this can be written as integral, this is integral px by qx times f of x into qx dx. So if you closely observe, what is this equal to? This is nothing but the expectation of px by qx times f of x, and x is now being sampled from qx. Okay, just observe this expression here. So whatever we have here can be represented as a function, and qx is the underlying distribution with respect to which we are computing the expectation. Therefore, this entire thing would be now expectation of f of x times the ratio of these two densities, and this expectation is now with respect to qx instead of px. Okay, so now what did we just do? We wrote the expectation of a function f of x with respect to distribution px as an expectation of the same function f of x multiplied with the ratios of two densities, and this expectation is now with respect to qx. Now this technique is what is called as importance sampling, where what did we just do? What is an expectation with respect to some density px is now converted into an expectation with respect to some other density qx. All that you need to do is you need to know how to compute the ratio of these two densities, the old density and the new density. Then the expectation with respect to one of the densities of a function can be computed as an expectation that is taken with respect to the other density qx, given that the function is multiplied by the ratio of these two densities at all points. So this is the result. This particular result is what is called as importance sampling. Now probably you would guess how would this be useful in our case. Remember that in our case what we were interested in is computing this particular expectation, right, of a function with respect to some distribution p theta. Now the problem was that we do not wish to take sample these trajectories from the same policy that is getting updated. So instead of taking an expectation with respect to the same policy that is getting updated, we will draw the trajectories from some other policy or some other language model in this case and keep it fixed. So that is the whole idea. And instead of using this function now, it will now become the importance sampling version of the expectation, the policy gradient update that we have. Now the next question is how to use this idea of importance sampling in the policy gradient theorem. Let us look at that. In the context of policy gradient theorem, in the context of the policy gradient theorem, context of policy gradient, so we have the gradient of the objective that would want to optimize. What was that equal to? That was the expectation of the gradient of log of the policy pi theta at given st times the advantage function at. This is what we had, and this expectation, what's important is to note that this expectation was with respect to pi theta, which is the policy that is getting estimated. Now suppose there exists another policy, pi theta old, from which the trajectories are drawn. Okay. Now applying the idea of importance sampling, what do we have? We have this expectation now, j theta, which is equal to the expectation of log pi theta at given st times at, and this expectation is with respect to pi theta is now equal to expectation of this function log pi theta at given st times the advantage function, multiply this entire thing by the ratio of the densities. This is what importance sampling showed us, divided by pi theta old, right? So now this expectation, the outer expectation now is with respect to pi theta old. So this is what importance sampling showed us, right? So just to recall, what did we do? So the expectation of a function with respect to some distribution is given by the expectation of that function multiplied by the ratios of the densities, and the expectation now is with respect to the new density q, I'm just applying the policy gradient theorem here. What we had, sorry, the important sampling idea here. What we had was expectation of some function with respect to pi theta. Now take this function, multiply it with the ratio of the previous distribution and the new distribution. The outer expectation is now with respect to the new distribution, in which in our case, which is pi theta old. Okay. Now this can further be reduced in a very interesting form. So consider pi theta at given st divided by pi theta old at given st times the gradient of log of pi theta at given st. Now this is equal to the gradient of pi theta at given st divided by pi theta old at given st. This expression is easy to verify. It follows from the definition. We have the derivative of log of pi theta, which is the derivative of pi theta times 1 by pi theta. So pi theta in the numerator and the denominator cancels off. You have the derivative of pi theta divided by pi theta old at given st, which is a constant as far as theta is concerned. Right? Now, what does this imply? This implies that we can define another surrogate loss function, define a surrogate loss function, let's call it L theta, that is equal to the expectation of RT times the advantage function at, and this expectation is with respect to pi theta old, where RT is the density ratio, so which is pi theta at given st divided by pi theta old at given st. Okay. Now what we just did was we defined another surrogate loss function. It's easy to show, that can be seen, can be verified that the derivative of this particular surrogate is same as the derivative of the surrogate that we had while we derived the policy gradient theorem at theta equal to theta old. So this is very easy to show. We just showed this actually, right? I mean, if you look at it, we use the important sampling. So the gradient of the function that we needed in the policy gradient theorem was simply given by this expectation, which involved a ratio here, and the expectation was with respect to theta old, and the expression that was there inside the expectation, which was this, was shown to be equal to the derivative of this density ratio. So let us write this as is equal to the derivative of RT. Right, this is the density ratio. Now, if we simply define another surrogate loss function L theta, which is expectation of this ratio times the advantage function, then it's trivial. We already showed that the gradient of this surrogate loss function is equal to the gradient of the objective that we need in the policy gradient theorem. Okay. Now, why is this important? In methods such as PPO, and DPO and TRPO, the surrogate objective is used. So this is why we need this. If you look at the expressions that are used for PPO, TRPO and so on, you would see that the objective function that is used will have this particular surrogate, okay, but not the form that is used for the policy gradient theorem. This is simply because the derivative of the surrogate is exactly equal to the derivative of the objective function that we need. So let us write that. Now PPO objective, no, not yet. So let's write this as surrogate objective. Let's call this as L importance sampled objective. So this L of LIS theta is equal to the expectation of RT, which is the ratio, times, write it explicitly perhaps. So this is equal to expectation of pi theta AT given ST divided by pi theta old AT given ST times the advantage function. So this is the new objective function that we have, which was constructed to solve the problem of on policy learning. So this expectation now is with respect to pi theta old, right? This is what we derived using the importance sampling theorem, importance sampling idea, where the objective now involves the ratio of the two density functions, which are two different policies, the old and the new policy, and the expectation is with respect to an old policy, theta old, that is not getting updated during the policy updation, right? Okay. This forms the basis for, this expression forms the basis for a lot of RLHF algorithms, including PPO. Now, let's start from here and slowly derive or improvise and go towards the policy gradient theorem, the PPO algorithm. Okay. Now, there is an issue with this particular form that we just looked at, which is that if in the above formulation, if pi theta deviates too much from pi theta old. Now recall what's happening. We get the trajectories from pi theta old, which is a fixed policy, and then update the parameters of the policy given by pi theta using gradient descent, right? Now, while doing this, if pi theta, which is the new policy that we obtain after gradient descent, deviates too much from pi theta old, which is the old policy, then the objective function explodes and leads to very high variance estimates. High variance estimates leading to instability. So meaning, while we are updating the policy pi theta, we don't want that to get updated too fast, in the sense that we don't want that to get deviated from pi theta old too much. Okay. So how do you ensure that that this does not happen? It's an obvious way. There's an obvious way to do this is constrain this optimization problem using some KL type of divergence constraint that would not let pi theta go too far away from pi theta old. That's the idea. Now, to avoid the above problem, the objective function is constrained objective function is constrained to restrict pi theta deviating too much from pi theta old. So how is this done? Via a distributional divergence metric. Distributional divergence